Our home. That pale blue dot in a vast cosmic arena. Teeming with life. From deepest seas to highest peaks. But in the past few centuries, we've made a mess. While humans are, without question, the single greatest cause of Earth's predicament, there is no one singular solution. Which is why many companies across the globe are taking bold steps forward and developing new, inventive solutions to renew, restore, and rescue our planet. This is Earth Rescue. Before humankind relied on fossil fuels, naturally occurring greenhouse gases like carbon dioxide and methane prevented the planet from freezing over. By trapping heat from the sun, these gases actually ensured that this little blue ball we live on remained habitable. However, as CO2 emissions rise, the delicate composition of our atmosphere is thrown out of balance. And the gases that keep us from freezing over are now causing global temperatures to rise dangerously fast. Climeworks uses technology called direct air capture to take carbon dioxide directly out of the air. When the removed gases are combined with underground storage, it allows for the permanent removal of excess and legacy CO2 emissions, helping to restore the balance of gases in our atmosphere.
We are providing a service, and the service is for people who want to mitigate climate change.
A PhD and chemical engineer, Natalie Casas has over a decade of experience developing absorption processes for CO2 capture.
Carbon capture is something we hear a lot in the media as a potential solution to climate change, but I don't know if everyone knows exactly what it involves. So could you run me through what exactly it is?
So direct air capture means we are taking CO2 out of the air. So we were emitting CO2 for ages, and now we have too much CO2 in the atmosphere and we need to remove it in order to level out the temperature increase, so to mitigate climate change basically. There are gigatons we need to take out of the air. For me at the moment, this is the biggest challenge humankind has. The temperature is rising. This might sound nice, but it is not nice. So if temperature rises, glaciers are melting, sea level rises, the weather will change, so the impact is huge. We made quite a big mess, which we need to clean up.
So how exactly do we remove CO2 from the air? How does the process work?
So our process is basically a metallic box, which we put outside. In this metallic box, we have a filter material. The filter material has the capacity to bind CO2. So what we do, we blow air through the box. The CO2 sticks on the filter material. You can imagine it's a kind of a sponge where the CO2 sticks on it. When the filter material is full, we close the box, we start heating, and while we heat, the CO2 is released and can be collected.
And so what happens to that carbon once you've collected it?
So there are different things you can do, but if you want to reduce the carbon dioxide in the atmosphere, you need to safely store the CO2. And this is what we do in Iceland with our plant called Orca. So we send the CO2 to Carbfix, which then pumps it underground, and in this basaltic Icelandic rock, it reacts to carbonates. So it's a very safe and permanent option to store CO2.
And that brings me on quite nicely to my next question, which is, can you do this anywhere, or do you need like specific rock types to trap the CO2?
The capturing can be done basically anywhere. But we have inputs, which is electricity and heat, and we have output, which is CO2. And we are committed to work only with renewable energy sources. So we need to be somewhere where renewable electricity is available. And then it comes to the storage part. We need to be somewhere where CO2 can be stored. Worldwide, you have many different locations where this is possible.
And you mentioned that this process requires energy, and that it might produce some CO2 emissions. in that? What is the ratio? What's the trade-off between how much you can pull in versus how much you produce in the process?
Yeah, today we are at about a carbon efficiency of about 10%, meaning if we capture 100 kilos, we emit 10. We know that we can go lower when we improve the process. So while we get more efficient, the CO2 footprint gets down. And some predictions we have, I think we can go to 5 to 3%.
Is that something that simulation can help you with?
Yes, indeed. So especially in this fluid dynamical context, simulations are very important. So we need to understand how much energy we need to provide to get the air through. And as you know, the CO2 concentration in the air is very low. So we need to blow a lot of air through. So this is a big chunk of the electricity needs we have. So if we would need to build a machine every time we have a new idea, this will cost a lot, take a lot of time, and with simulation this is done in, let's say, 2 days.
What we're looking at is a simulation of the impact of the outside environment on the possible future concepts.
Right, so basically you're putting air in, you're taking CO2 out, it's in the filters, and you push that air without CO2 back out again, and you're trying to find a way of not having that air without CO2 being pulled back in.
Precisely that. And simulation allows us to do it without building a physical prototype and assessing the possible environments or wind conditions in different parts of the planet where we might put our product later on in the future.
I think in the last 2 years, I would say, a really big change has happened. So more and more big corporations really want to make a difference, and they realize, hey, if we want to be net zero, this means something. And we really need to act today in order to help the people to scale this industry up. So this is really the wind has changed.
Space exploration, arguably the greatest accomplishment of our time. Not only has it expanded our horizons, but it's also allowed us to communicate almost instantaneously across continents and develop tools like the internet or GPS. Unfortunately, it's also left a potential disaster in its wake: space junk. Floating miles above us are layers of debris, dead satellites, and discarded space parts, which could render certain altitudes almost unusable by most space agencies. And with orbital activity accelerating, it's more important than ever that we become good stewards of the space around our planet. Astroscale is helping us do just that by developing scalable solutions to create a sustainable and safe space environment and mitigate the growing buildup of hazardous debris surrounding the Earth.
Most people don't realise how much they depend on space in their everyday lives.
Al Colburn is the head of spacecraft operations here at Astroscale. An aerospace engineer, Al specialises in all aspects of spacecraft operations, preparation and contingency recoveries.
It's absolutely essential to lots of things that we take for granted: GPS, data transmission, research. Space is our best resource for all of these things.
As I understand it, you guys are basically trying to clean up space. So could you tell me a little bit about why you're doing that and kind of the scale of the problem?
The reason we're doing it is that it's a growing issue that we need to tackle as humans do. We've started using an environment, the space environment, and not really thought about how we're going to take care of that resource for the future. So it's really important that we address the growing problem before it gets out of control like it has done in other areas.
Obviously the space age started in the 60s, we've been putting stuff up there, but we've been doing it, as I understand it, without much thought about what happens once it's up there. So is it just a case of not thinking about these things before we do them, or are there more elements to it?
Over time, the number of launches we've executed each year has increased significantly. It's partly that originally no one was thinking about how they would be responsible for the full life cycle of their mission and how they would bring it down or deorbit it at the appropriate time, but also missions fail and you have to be able to deal with this scenario as well.
So let's talk about space junk then. Like, can you give me a sense of how much is up there and the scale of the problem we're dealing with?
We currently track about, more than 30,000 objects that are bigger than 10 centimetres in diameter from ground. We can see those ones, but what we can't see is all the smaller objects, which we know there are many more of, including millions of pieces of debris that are of millimetre size. So.
And those can still be problematic, right? Like a small piece can still cause a lot of damage.
Yeah, absolutely. Because of the impact velocity, it doesn't need to weigh very much to have a massive impact on what it hits. Even a paint fleck has hit the International Space Station and cracked the glass window of that. So these things do happen, have a big effect. Yeah.
The fact that you say like even a tiny object can have catastrophic effects, that makes it all the more important, clearly, to clean up space. So how do you even go about that?
At Astroscale, we're studying various solutions to different facets of the problem. So we've got the problem of spacecraft which have reached end of life or become inoperable. Then we have life extension services, so extending the life of any assets that are in flight which are still operable. So they may run out of propellant, but that doesn't mean that the whole thing is worthless. So if we can go and dock with that and then control it with a new propellant resource, then that's obviously better for everyone. The third point that Astroscale are addressing is active debris removal of other space junk.
What are the challenges involved, and how do you make sure that you align well enough to dock?
All our mission types use the same technological developments. So the ability to rendezvous with something that's already in orbit. We have to launch a spacecraft and then match our orbit to that one and gradually reduce the distance between them. And then when we get close enough, we transition from that phase to a relative navigation phase where the servicer spacecraft can actually see its client and react to the distance between them and control its approach autonomously. So this is the idea, and this is the technology that then applies to end-of-life services, life extension services, and active debris removal. Once you can achieve that, you can apply it to all sorts of things, including in-orbit manufacturing, in-orbit refueling, all these other aspects as well. So this is the key thing we're trying to develop. And
so tell me about the stage at which you're at then. You mentioned that you've launched your first mission, so could you talk me through that in more detail?
Yeah, so the concept of LCD is to demonstrate increasingly complicated phases of rendezvous and capture. So we took a simulated piece of debris with us, which was docked, so the two spacecraft were docked during launch, and then in our first demonstration we released it and just made a linear capture of it with our servicer just to prove the concept of our magnetic docking system in flight. And then in January of this year, we attempted our first kind of longer range proper capture using the onboard sensors of the servicer to analyse the dynamics of the client and rendezvous and dock with it. We use various simulators within the phases of mission development and execution. It's very important that we can test our software on ground and iterate it and develop it this way.
Why has it taken us this long to think about this? We've been exploring space for decades, right? And why are we only now realising actually we need to take care of it?
Yeah, I think it relates to the phenomenon of the kind of rate of commercialisation of space that's going on at the moment. So I think we have something like over 100,000 spacecraft planned to be launched over the coming years, which shows you the scale of the problem. It's becoming a sort of realm which is not unique to the kind of major institutions, NASA, ESA, these people. Now there are commercial companies offering services, and there needs to be a kind of overall regulation structure so that people need to buy into in order to control it for future use.
Trash. We've got loads of it, and it's piling up. But even the best municipal recycling programs leave something behind. Fortunately, companies like Enerkem are doing something about it. Enerkem's disruptive technology converts non-recyclable, non-compostable waste into biofuels and other useful chemicals, extracting every ounce of potential from our rubbish. And they're doing it all with better economics and greater sustainability than other technologies that rely solely on fossil fuels.
We can synthesize quite many things out of it. Syngas is literally a portal to produce many products otherwise produced from fossil fuels.
Awesome. I mean, it sounds like a really good intermediary step to getting off fossil fuels entirely. An engineer and PhD, Mikhail is drawn to exploring the real world in its virtual counterpart, using simulation to predict and see through walls. He's built his career on the successful application of numerical simulation in industrial contexts, improving plant operations and designing better equipment for developing new technologies. Gasification reactors and peripherals, like those at work here at Enerkem, have been his biggest playground thus far.
This is what we call municipal solid waste. This is a material that we produce at a rate of 2 billion tons per year globally. In high-income countries, we recycle up to 1/3 of it. The rest, it goes to landfill mostly and incineration.
So 2/3 of our waste just goes straight into landfill?
2/3 of it straight to the landfill or incineration. It's basically lost.
I think most people know on some level that as a society we're incredibly wasteful, but I think perhaps most people underestimate the scale of this. So what can we do with all that trash that we chuck out?
Well, this trash, from a microscopic point of view, it looks useless, but from a macroscopic point of view, this has value. It has carbon, it has energy in it, and a better way than incineration or landfill is to tear it apart, maximize the recycling and the composting first. Then what remains out of this operation, we call it the waste of the waste. And it looks like this. It's a fluffy, heterogeneous material, still lots of good carbon and energy in it. What do we do with it? We do this. This is methanol, a biofuel.
So you're turning this waste, which is otherwise useless, into this?
Exactly.
How do we go about turning this into this?
There are two global steps in the process. The first step is to deconstruct the molecule. This step we call it gasification. So we will expose the material to high temperature and breaks the molecules, going from complex to simple molecules. Basically 3 molecules: hydrogen, carbon monoxide, and carbon dioxide. Then we reconstruct new molecules. And the second part of the process is basically made of catalytic reactors. This is where we rebuild new product like methanol or ethanol or other things like sustainable aviation fuel.
You can make plane fuel out of this?
Yeah, we know how to make plane fuels out of this.
So let's talk a little bit more about gasification. You mentioned you're turning this into gases. Why do you need to do that?
We need to do that because it's so heterogeneous there's no conventional process that can really efficiently address so many different things. The only solution to this is to deconstruct and reconstruct. And gasification really shines for that purpose.
And so how do you actually gasify it?
It starts with a fluid acid bed reactor. So there's sand in fluidization, it has good temperature. We introduce this feedstock, it meets the sand, get gasified, and then the gas will be upgraded in a second gasification step, completely deconstruct the molecules. We will convert up to 85% of the carbon in this material in the product. For this project, to the design of this plant, we did about 10,000 simulation. 10,000 simulation with the Ansys product. CFD, DM, FEA, we do a lot of simulation.
So what kind of things are you simulating then?
Here we have a notable simulation example. It represents the fluid acid bed reactor, the gasifier. The physics we're seeing here is this ascent into fluidization, and we see the feedstock being introduced in the reactor. So we can appreciate qualitatively how the bed is mixing the feedstock.
Why are you mixing sand and feedstock together?
In this reactor, the sand functionality is to get the feedstock mix and heat uniformly. This is another visualization of the same simulation that provide more information on different physics. Here we see the temperature map, and on the right we see a gas product that is produced during the reaction. In this animation we see there's some temperature gradient, which is a useful information for us. This is something we want to control properly. Another useful metrics for us is the segregation index. This index quantifies how two solid phase overlap in space. For example, sand and feedstock. And here we see their spatial distribution along the height. The segregation index is based on the spatial distribution. And it tells us, in that case, that the two phases are not much segregated. They are kind of together. This is another useful information for us. So what next? What do we do with this information? These performance metrics are very useful when we do parametric study. Parametric study is very important to get the most out of the simulation power. We call it predict, explore, optimize. Once we have a valid model, we use it to explore. This is where we accumulate a lot of simulation, the parametric study, automatize. And this leads to optimization.
We can't undo the past, and the scars we've left on this planet will remain for centuries to come. But combine our greatest minds, boldest innovations, and game-changing technologies, and we will turn the tide and begin to make our impact on this blue planet a more positive one. When we continue to develop inventive ways to clean up our mess, forge daring new pathways towards carbon neutrality, and avoid repeating past mistakes, we can rescue our Earth.